Okay, I just misunderstood that.
It is weird, but like Garrett and I have been like pinging messages back and forth. How the fuck does this work? And then we're like, he's having like first I don't understand something, he's explaining it to me, and then he doesn't understand anything, and I'm explaining it to him, trying to like sort of.
You can go to the last lab because I had a midterm on Tuesday, and not enough time to learn for that.
Don't worry, I'll help you.
Oh, that's also the matrix. Should return the matrix that translates both coordinates
into camera coordinates.
But Jackson matrix is the one that does these. Should do these new steps, but now just.
No, it's just one thing. And then after after you do.
Your objection is like the results.
I'm really hungry. I don't know why. Breakfast is really and then what you do is after you've done that, make sure you divide the x, y, and z by the w. You do the perspective division. Divide x, y, and z by the w.
Yeah, it's like
It's this bit here.
Okay, so I projected in
I don't know if you can do that.
from raw to camera.
Alright, so first, so what I do is I guess first thing you've got to do is create a homogenized version. So you take the vertex position and stick a 1.0 on it. Okay, then view matrix, then projection matrix. And then afterwards you do the sort of divide by fourth value, right? Which is going to be something. And then you get something which is looking like this, except it won't look like this. It'll have colour. This just looks like this because I'm still doing flipping, and it's not quite, I'm still flipping.
I will just have the rest because
Well, actually, no, you just get the vertices, but yeah, and then you do rasterizations.
To be fair, like, even I had no idea to do that. Let's try
that makes me feel.
Hello, Garrett.
I don't know how we should
Hello, Matteo.
extract this from the slides. I don't think.
Oh, work out.
Garrett, have you got any food?
If you count tea bags,
Right, hello. Thank you.
Oh yeah. Let's do Friday, right?
I was the same stage as you.
I'm just like,
No, I started last night.
I was reading it before.
I'm doing fine, I'm just working on it. Oh.
And then I found this.
Oh
Oh my gosh, same. That's me last night. I was just googling.
The projection matrix for me doesn't do anything at all. It doesn't actually do anything.
I wrote it down. But yeah, I just love you.
It's just like ones and a zero. I don't understand. Yeah, because I did that.
Not really.
I did that. Well, I think I paid all the 3, and they don't do it. No one I can't find, they don't change anything. Which is weird, right? Because I'm multiplying by something.
Yeah.
Not changing anything.
No, mine had 2 weeks.
We get 3 months right for every human.
Yeah.
3 marks for every 2 months.
Yeah, so basically there's a cap on 100, but because what did they cut off?
The initial. So that's like 2 weeks.
So it doesn't really affect me.
Well, you get like a lot of
Yeah.
Which is great, yeah. But
It's
like,
good to have
it didn't put me out.
That's in my time last I did.
So you can get over 100 seconds.
That's just the clip.
I don't know what I mean, yeah.
So yeah,
I still don't know.
Yeah.
See, that's all fine.
like
It doesn't work. I don't know why. Because the polygons are there. Look, I have to write code to make this work. I don't understand this. Right? Is this basically... I'm going to take the polygon and it has all the points here. I think it's right? What if I content now? Look what I hope.
I need colors, highlighters, purple. Always one down.
I know the fuel.
People like you have like
So many free pens here.
yeah, that's how my pens run out.
I'll never have to buy a pen there.
Why? Look. See? Same thing.
Like this.
You type it in the same position.
I'll stick canvas and like and Raj just not have the nice because how we choose
I wrote mine as well.
It's weird, that one. Yeah, we've done that.
This is so small. Mine's like
It's like 7 states.
I'm doing like less efficient.
I think I'm going to work at this.
Check over my stuff. So all I've really done is say, yeah, that makes sense. Which is difficult to like all the questions in the last section are
Yeah, how are you?
say basically.
Long time no see.
And then I managed to train too.
yeah, that's not like
yes, if the string is less than 5. And that's not the decision is the boundary that a Turing machine can decide to comprise of like so if it was just is this strings less than 5 is this decidable, I'd be like, well, yeah, it's reasonable. But then it's like, it's a Turing that is like, so I say, but when ready to go, my main contributions are nodding my head, saying, yeah, that makes sense, and I came up with more efficient URL for the subtractor thing than David had, so I'm quite proud of that. Nice, you can install VLC media. I'm saying you can install VLC. So what you do is take the vertex, multiply it by the U matrix, the camera space, and then multiply it by that one you just showed me, and then you apply the X, Y, and Z values by the W.
It's like this. Oh, that's pretty.
I have no idea which is
It's ridiculous in this matrix. No, it isn't. Okay, sorry.
Okay, well, you want. We should do like bringing it up to date. Yeah, like it's expensive to have like one sticker. Oh, they're so rich, I just give us they spent about 1 day just for one. Why? And it was a cake at the parents' school.
Why is the picture in the laptop?
Because you don't have a laptop. Oh, well, it was for flexibility. Oh, it wasn't changed. It was like, it was so hard.
I came just for the party.
I did that as well.
Ready? Hello. Okay, welcome back. At 15 today it's the rendering equation. What's that? Good like this for 6 hours? Oh. Okay, so enjoy that little I can remind you time short. Rendering equations, so if before what you heard is too much computer and not enough maybe science or math or theory or formula or something that you think you can maybe learn from the internet. There's lots that you can learn about how OpenGL works on the internet. I told you some is outdated, but today we're going to really talk about some equations. Because what you usually get when you run OpenGL, if you follow the model, like the classic OpenGL model, if you're taking rasterization, you will get images such as this. This is Phong. You have your objects. These are geometric objects. You have a light source. Maybe there's a shadow. This is roughly the quality that you would get. Of course, you can get better than that, but this will only be possible by use of textures and so on. So if you add lots of geometric details, it will look more rich, but the lighting quality will not really get better than this. Yeah? And today, we want to talk about how to turn this into something slightly better. So this is not my images, but somebody also added textures, which is a bit unfair, I would say, because this we would know how to do in OpenGL as well. We just saw this last week. But on the other hand, there's also the light distribution in the room, which is much more advanced. So you see things which are maybe softly reflecting. You see those reflections, and most of all, you see some global light distribution, and this you will never get from OpenGL. It's not so much about if this is a particularly good image, but you should remember roughly what the change was from the image that you saw before to this image. These are the things for today. I still feel this microphone is not helping so much, so please somebody really tell me if it's adding more noise than I think it stops sometimes, doesn't it? So if maybe somebody tell me in the end if this is doing more harm than better. I can't hear it for myself, so I do hear myself, but I feel it's not like super good. So tell me maybe in the end if I should change that. Okay, I also want to remind you that at the beginning we said there are different types of light transport. There's this diffuse specular transport, which is... I will stop with this microphone, I maybe give myself too much. Or is it something I should know? This is not... I think in the end on, what is it called, lecture cast, I do still hear myself if I do speak loud enough because I do hear the audience, so if it really doesn't work, we will have to check, but with this microphone I think I can't. Okay, I'll try to remember to speak loud. Okay, so different types of light transport. We have seen that if light arrives at a diffuse surface, and then it's again visible in a specular surface, that's a typical configuration. Light is coming from somewhere, that's the light source, we see it here in the little mirror. It arrived at the wall, it got reflected diffusely. We heard the theory of how this works, you can simulate that, and your ray tracer can even do this because it can do the reflection of this diffused wall in here. And the trick was to use like exactly a single ray that follows the laws of a mirror reflection to get to know that this is this point that you see here, and then you take that value and you will be good. The same trick also works for specular. So if there are multiple such bounces, so you see some piece of metal in a piece of metal in a piece of metal as much as you want, if you program this correctly, you can still do the trick. If in the end, later on, if you continue this path, there is something diffuse. What it will not do is like specular light. Because for a point light, it's infinitely small, so the chance of hitting this with the ray when you just continue with your traditional ray tracer is 0. So that won't do. But in the end, there's usually something specular, and then it can do. What it could not do is diffuse. Yeah, because you were sending exactly one specular ray and then it went on. And what diffuse would need is for many directions, many other directions. And this is something what we will be able to do today. And even more advanced, it's a bit complicated to tell these two guys apart, but this is called the specular diffuse transport, because what happened here to form this little, what we call caustic, this pattern of light, the light was first hitting something which is like a mirror, which is reflecting the light in exactly one direction, and then it got visible on a specular surface. That's not the same as if it first hit something diffuse, which looks the same from everywhere, kind of easy, and then you see it in a mirror. So this is also much more rare, but look out for this whenever you have something specular and then you have those light patterns forming here. This is called the caustic. You can have that for metal, then it's called a reflective caustic because light got reflected, but at the same time you can have it for refraction, which is the typical glass mirror ball magnification glass situation where you have this burning behavior where light is focusing. All this is called a caustic. So these things are pretty hard, but the theory of today will cover off how to do this. Yeah? So and again, orientation where we are. We have started here because it's somewhere in the middle, ray tracing. It's not like a correctly formal name, but what we did there in the beginning is maybe not super fast and not super slow, and it gave you some amount of realism. What we then saw is how to make it faster. This is not uniform. Yeah, it's much, much faster. I think these days with OpenGL you can achieve almost the same amount of realism with a few tricks, maybe even more. But what we're interested in today is the theory behind something which is then an implementation that allows you to make it even slower. No, that's not what you want, but to make it even more realistic. Yeah? To have these types of light transport that you didn't have before. And if you understand the theory well, maybe also allows you to do it faster, so to move this thing to the right. Yeah? But this requires understanding the theory a bit, so we will spend the full hour today, or the rest of this hour, explaining the rendering equation, giving the definition, thinking a bit about what light really is, introducing a few quantities, for example, reflectance, a formal notion of BRDF, that will resolve a few of those questions that you had with what is glossiness of a metal object. I was asked this many times, then you had questions, so this will really answer it, I hope. You will hear about how the time, length, and spectral domain are related to this. This should be new to you. This is all the theory for today. And then most of the other lectures that I will be doing in this course will talk about methods to solve this. So this will be 1 plus 2 hours where I will discuss this through practical implementations, path tracing and photon mapping, of how to solve the equation. So physically based rendering, this is what is basically the method that you will use the theory from today for. It's the simulation of light transport, and for this you should wonder a bit what light really is, the nature of light, how it's really traveling, and how it interacts with material and geometry. And it's always about those 3 players, and understanding this is the key to simulating this successfully. So let's really just recall what light is. So visible light is electromagnetic radiation with wavelength approximately in the range from 400 to 700. It's good to remember that. Maybe some of you know roughly of how to convert this into RGB values. Just to remind you, R, G, and B is not like taking a fixed value and simulating it at that wavelength, but there's something like basis functions of devices and so on. I'm not sure if you learned this in image processing courses. There's a lot to it. For us, there are different ways of doing this. When you now did RGB, that meant that there is a function that says it's a bit more important in the red part of the spectrum, and when you did green, it's a bit more important here. And what we might later want for certain purposes is to simulate exactly one spectral wavelength, which is then in the visible range. Yeah? And there's no point in simulating anything else. And it's good to remember this because there are certain aspects about wavelength that you should better ignore and then be more happy in simulating that. So there's a bit of confusion. There's something called photon mapping around that confuses people, and people might think it might be a particle phenomenon which we're simulating. Not at all. So what we do here, we will not take the view of wave or particle, but we really stay in this vanilla high school setting where light is just traveling straight lines with infinite velocity, and we treat it as a continuous phenomenon. If it has a certain speed, we're not interested in simulating a renderer that will turn on here the light and then computes like the image like whatever nanoseconds later or something. You can do this. It's an interesting exercise, but for us, this is one of the key assumptions. You just assume it travels straight. We ignore basically all wave phenomena, which basically sets us on a certain scale. Same as sound on a certain scale has diffraction phenomena. Light on a certain scale would also have diffraction phenomena. So if you want to use the theory from today to simulate your, for example, microscopic image formation, that would not be that good. But on the macroscopic scale with cars and humans, wave phenomena for light for that wavelength are sufficiently small enough, and then we ignore them. So no wave phenomena here, it just travels along the most easy way you can assume. Yeah? And so this simplifies everything, but we must be clear how we really simplify. And there's a really large number of radiometric units, and previous editions of this course have explained them all, because previously there was a method called radiosity, which traditionally is like a very good method for certain conditions to compute solutions to the rendering equations. I learned this also by heart when I studied, and I had to learn all those radiometric units, so I think it's like 10 radiometric units, and you also have the perceptual equivalence, how strongly you perceive a certain quantity of light over time, angle, and all of these things. So that's around 20 units. And again, that's easy to test, so I can very easily set up an exam where I ask you, okay, give me the units of radiant flux. That's one of these units, but it will not teach you much. And so today I will just simulate exactly in one unit, which is called radiance. And whenever you're setting your values, when you didn't know before what it is, when you say diffuse times light color E plus plus, or when you iterate over your lights and so on. So my suggestion now, if you also take it to the proper theory, what you're doing there is you work in units of radiance. And what it really is the quantity that is high if you look at a bright point. That's very intuitive. Yeah, that's usually what you would expect from an image. If the value is high, this value is high. And there are other such. Yeah, you can integrate over the angles, like how bright is a point from all the angles. And if it's then view dependent, it might change when you're looking at it, or you could integrate over time. Yeah, so then it would be bright if it just was very flashy, and then over a longer extent of time, the number of photons might be the same. Yeah, if I shoot 1,000,000, like for a very short minute of time, or I shoot it for a longer time, there are lots of domains over which you could integrate, and all of this is to be ignored. Integrate over space, or all of them at the same time. There's lots of entire zoo of things that you can think about. But at this point, we're really interested. You take a point and you look at it from some direction, and when it's bright, this value is high, and it's called radiance. Yeah. And yeah, so how many photons? And you fix at a certain wavelength per unit time, per unit area, per unit solid angle. Yeah, so it's not interested how it looks from somewhere else, or how it looks next to it, or how it looked 5 seconds ago, or integrating over any of these things. Not at all. It's just at that moment for this particular infinitely small piece of wavelength, for this infinitely small piece of solid angle that you look at it, and then you call it radiance. Yeah. And there's always this sentence, this is another thing to remember, it does not change when moving along this direction that you're taking in free space. And people usually say it and nobody records it, so I made a little drawing that tells you if you are somewhere in space and you're looking into a certain differential solid angle, this is infinitely small, and you move along that direction, you get true values, and they are the same if you travel to induced space. That's one property of radiance. So wherever you go, if this is the color, it will be the same. Yeah? And that's a fundamental property that you need for those algorithms. It's of course changing if you go behind the cat, or if you go into a different direction, or you go over time, or any of these other things. But this is this thing under which it is invariant. If you move, this is not going to change. Okay. And there are a few other simplifying assumptions, and I talked about wavelength in the beginning. So there is no interaction between wavelengths. If there are interactions, this is called fluorescence. So what never happens if I send something in at a certain wavelength, it comes out at a different wavelength. You can imagine that due to, I don't know, fluorescence here. There are certain materials that do this, even with time delay. That is called phosphorescence. Most phosphorescences are also fluorescent. So you send in light at one wavelength, you wait a certain time, and it comes back at a different wavelength. This is fun to simulate, I do this, but it's not for here. So here you can really assume I send in a certain wavelength, and I get this wavelength that I send in back, and it's independent of all the other wavelengths, so it's also nice to parallelize. You do RGB, very old-fashioned, but you have to be clear, if it was not, it would be called fluorescence, and if it was time delayed, it would be called phosphorescence. Ah yeah, you already have the second one. So the solution is valid over time unless the scene changes. You have the scene as it is. As long as you don't move or the scene doesn't change, the lighting doesn't change. Would not be the same for phosphorescence. If you have a room with this glow it sticker, you shine light at it, you wait 5 seconds, you get a certain image, you wait another 5 seconds, you get a different image. And that just says we ignore this, and this is time invariant. Okay. And yeah, and then the last one is the one with the kitten. So interaction only occurs at the surface of object and nowhere in between. So if you were in fog, for example, if you have the kitten and you move just more and more far away, it will get grayer and grayer, yeah, because the medium in between it is longer and light is being absorbed and scattered at many things. So this is the final simplifying assumption. This is a non-participating medium. It's pure vacuum. Light just travels. Very basic. It's never being absorbed or emitted or scattered anywhere in between. Yeah. And you have to make those simplifying assumptions, and until 1986 it was not really clear which one you can make and how you should do them and so on. And then there was this famous equation of this guy Kajia. He was with Microsoft Research back then, and he still is, I think. He's even still doing things. And he, for the first time, set up this, what we call now the rendering equation. And what it says is if you want to compute images which have all those properties, and in this setting, under these assumptions, can predict how something looks like when I give in certain variables that tell me how my scene is organized, I will give you as a solution a radiance distribution over space and angle. And if you're able to find this solution, the solution of this is the solution to the entire rendering problem. There is nothing else, if this, of course, inside this model, but then you are complete. There are no other things going on. Yeah? And each approach of rendering is a different type of solution to this equation. So even OpenGL that you saw is, when you look at the equation, and there are integrals and very complicated things, but if you turn that into sum and simplify enough, even what you saw in ray tracing or OpenGL is a solution to this equation. If you simplify everything enough, at some point it will be the equation. Just say it's a constant, that's a bit trivial, but it's like a non-trivial reduction of this rendering equation that would even give you OpenGL. And there are many that can do this, so I should maybe really start with maybe OpenGL even. There's finite element methods. I will not teach these. I find them a bit out of fashion. They are good for teaching and easy to teach and very didactical, but they're almost not used in practice anymore. The shipbuilding people down here in the floor, they will not agree. They will use finite elements to compute forces. So when you ever won't need to run simulation on other kinds of radiation, maybe antenna or ships or both at the same time, they maybe use finite elements and they solve similar equations. But for light, it got a bit out of fashion. Yeah? So what we'll do instead is Monte Carlo. People these days believe that Monte Carlo or path tracing solutions, they might really in the future, they are very simple to program and very easy to understand and yeah, much nicer to program. And they are preferred, and they will rather be the future, if not already used now in modern films. And there's another variant of this. This is very good if you start from the camera, and all of the complexity is due to complexity of effects that are dominated by your camera. But you might have also very complicated effects on the light side, so that it might be very complicated to understand how the light even gets from the light source to the camera. And in these conditions, there are other variants called density estimation. They basically turn around the computation, and they start from the light instead of starting from the camera. You started your race from the camera, where you set up your projection matrix, you send the ray to the pixel center, and you hope to find the way to the light. That's not always efficient. You could also go the other way around. You could start from the light and just try to find out where you end up on the sensor, and this is the other alternative. And I will also teach this, because this is also being used today. Yeah. So questions so far? Because no equations comes. Questions come. Okay, here it is. So what Kajia said is, what I'm interested in is the amount of radiance, so how bright the point is, when the point is here, and I look in a certain direction. How do you parameterize this? We will see later, but now you can imagine this is a three-dimensional point, and this is a three-dimensional vector. In fact, it's infinitely small solid angles and infinitely small units of time and volume and so on, but just think about it as a point as a 3D vector, so maybe a six-dimensional thing, just vector pointing in a direction and the location where you are. And what you want to have is basically this function. So it's not like a single value, but what you're interested in is finding the full function. It's not like computing this, because you will later see that this thing also appears here on the other side. It's just in a different position, and that it's not about just computing a value of something. It's about finding an equation finding a function that satisfies a certain equation. And the equation says, so if you want to have this is the radiance from a point, as I said, on a surface. I said that, but maybe ignore it a bit. You could have it everywhere, but usually you're interested in having it on the surface, because this is what you really see. But you could also do it for an arbitrary point in space, and you want it for a given direction. I stressed this many times. It's not like you have a point in space and it always has a certain value or color. It depends on how you look at that point. Yeah, it really changes. So that makes it 5D. If you want to have that value, it has to satisfy the following properties. One input to this entire thing is the emitted radiance from a point, again, somewhere in space in some direction. So you can say, when I'm looking for that value, there would be another function, which is input to the system, that just says, when I'm somewhere in some direction, there is light emitted in that direction. This would just tell you, when I go to that point and I look at that direction, will it be bright or not? You can imagine this function is rather dark. It will usually be black everywhere in most of the places, except where there are light sources. This will just tell you, for a certain direction, there's light coming into. I will have lots of examples for this. So this is input to this entire thing. It's not something you solve for. It's basically some kind of constraint when you say x plus 5 is something or something, so the 5, it's a constant that goes into the system of equations. So this would be rather easy. So in this case, for example, if you don't do all of this over here, it would just ask for a function that says these two are equal, and then it's obvious that this one would be the emission. So this just says, if there's nothing happening, I will just look at the emission directly and light would not bounce. That's boring. So there's more happening here on the other side. And this is this entire part, so you should see it as two parts. This is being emitted, and this is reflected light. And reflected light is much more complicated, regrettably. But yeah, what it does qualitatively is that you're summing the contribution from all other surfaces of the scene, or you're integrating over that. So you maybe remember you had this little loop over all the lights, and you're gathering lights from them. That was a very simplifying assumption that said, when I'm somewhere, there are like 3 individual points that I can look up, and then I sum over them and I get everything that I need. Yeah? And this is just generalizing this. Instead of looping over discretely many light sources, it says I loop over continuously many other directions. So the integration domain now is the spherical domain. I will go into detail. So when you're somewhere and you want to have the idea how much light is reflected here, you integrate over all the directions, not just light sources. There are no light sources in the system. Forget it. Yeah, I will say this many, many times. Light sources is a ray tracing OpenGL thing. Forget about light sources here. Yeah, you have to integrate over everything. Everything can become a light source. Yeah, because light maybe from a light source bounces somewhere and then it's bright and then it will still illuminate other points. Forget about light sources. Yeah. So this just says integrate over all the other directions, and then there are 3 factors in this one, and they will basically tell you how all those directions that you integrate over are interacting. So the first one is one of the things that makes it really complicated. It says you have to take this function that you're looking for, and you have to take that function that's defined everywhere. And you take the value of that function at a different point, which is called y. And this point y is exactly the point that if you go into that direction over which you're integrating and you end up somewhere, you look up how much light is descending to me. So you have to imagine you sit somewhere and you look into all the directions that there are. You go into every of these directions, you arrive at a point which has a certain distance, and then you check that value that arrives at you at your location. And then you do certain things with it, and you look for a function that satisfies all those properties. So don't be confused that this has a different name than the x. It's still exactly the same function. You're looking for one function with that property. And because light is being sent in that direction, when you look it up from here, you go for this minus. But this is the integration domain. So you're looking over all of these values, and you're finding always those values y. Compute the radiance and point y in the direction of the radius. Yeah. I will go into detail of all of these components later on. Yeah. And there's another thing, and you didn't hear about, but it's important to understand, that's pretty theoretical. This is not saying I sum up all of them, but what you're in fact doing is you're weighting them all with something called the reflectance function or the BRDF. And it's even more complicated because this is a function that might vary over space. So it might be different here and it might be different here. And it has 2 other parameters that just tell you, they translate, so to say, when light comes from a certain direction and I look at it from a certain other direction, how much of this is being reflected into that direction. Yeah? So for a diffuse surface, for example, this is a constant because it's irrelevant where the directions are coming from. All of them are contributing in the same amount. And for a mirror, this would be a function which is 0 almost everywhere, except if omega I and omega O, or the other omega, are exactly in this mirror configuration where all the light that comes in here is also going out in that direction. Yeah? In reality, it's just not infinite, but it's just very peaky, very selective. So it ignores all the light coming from all the directions except this one that is coming from the mirror. Yeah? Mirror direction. Okay, and this is the BRDF. We will go into detail. There are other variants of this. I will not explain so much where this guy comes from, because if this guy is constant, and I move a light source, there are no light sources anymore, but this value where LE is non-zero, I move this around, the entire thing would not change. And we saw that when you have a white piece of paper with under diffuse illumination, remember that, if you move the light source, the lighting does change. If I change my head, it does not change. But when I change the light, of course, when I shine on something from the top under Lambertian illumination, it's bright, and when I shine from below, it will be dark. Yeah? And this is this term here, this angle basically just says it's the angle between the normal at that point and this one, and this has to do with the fact that you're integrating over the spherical domain and so on. Yeah, but it's not part of the BRDF. So everything basically covered, and OpenGL is just a special case of it. I'll go into detail for all of these components in a second, but I just want to remind you again, there is no image. So if you want to compute a fancy image of this one, you should now, after thinking about that equation and thinking about it on that level, always wonder, what is a function Lx like, where x is moving around in your scene, and tells you that you see something under a certain direction. I cannot draw this direction for which you want to know Lx. It's like the thing that goes into the image, exactly those arrows that I cannot draw in that image. It's exactly, you arrive here from that direction, and you're interested what comes back to you. So this is this omega that you want to compute for. But overall, you're looking for that function, and what's the input is some other quantity that is the emissiveness that says everywhere how much light is it sending into every direction, and it's defined everywhere on your entire scene. So it's like a daunting task of computing this very high-dimensional, 5-dimensional thing. When the yellow thing goes in, you want to have the black one. No? Question? Yeah.
Doesn't this get extremely complicated?
Yes.
If I did this, so if I want to define a function for basically for the entire scene and for every
Yes.
surface, and I just maybe I'm a bit stupid with this, but I can't see how we can solve this in any reasonable time.
So it has certain dimensions why this is complicated. So something is maybe this output sensitiveness. So usually you don't want to compute a function for lots of things that you don't even see. So you could say, okay, why do I need to know what's the value of that function down here? Yeah, but you do not even see, because in your ray tracing you computed a function for the stuff that you immediately saw. But in fact you didn't, because if you have a mirror object, you already see objects in other places, for example, that were not in the image. And also we saw the fact that maybe the highlight in the mirror appears in different places. I talked to different people about this. You should maybe check in reality and so on. If you see a mirror ball and you see highlights maybe on a plastic ball, and you see the plastic ball directly and you see it in the mirror, the highlight is on different places. That's really scary, but it's clear because the mirror ball sees the thing from a different angle. There are certain people I talk to about this thing. So, and these are lots of examples how many different exotic X and many different exotic omega contribute to your image formation. And if light bounces enough, everything contributes in some crazy way. So you won't get away without it, and that's why you need to compute it. And there are lots of little tricks of how to do this. Yeah. And yeah, I will make a bit more explicit what are even the other complications that you have. So for example, that it's an integration in the spherical domain and so on, and that the right-hand side appears on the left-hand side, and how can it, and so on. Yeah. But I try to show it in its full complexity, because sometimes people just say, you compute this equation. It's not like you have a value and there's a lot of integration going on, and integrations may be hard, and I don't have an analytic solution. That's not the full problem. The problem is that you want a function that then, if you do this hard stuff, satisfies the constraint of the entire equation. That's even harder. It's not like in math where you give like some complicated expression that you have to simplify to get the value of the integral. Yeah, so give me the integral of sine of x of tangents, and you're done. It's like it also appears on the right-hand side and lives in a very complicated space. So let me recap that. What are the players going into this thing? It's the emission in the beginning. We should talk about how to define this, because how does the light even get in? It's the spherical integration that stresses people. And then visibility is also somewhere, like sending a shadow ray. Where is it now? You had your shadow ray. How are shadows going into this? Shadows go into it by finding y, which then just send you black things. That's what a shadow has become now. You just go in a direction and there's no light coming. That's now called a shadow. And if certain y, or just maybe the backside of something dark, these shadows will start to appear. If the y is exactly in such a direction that now some light that was there, if it hadn't been there, is missing. And that's now a shadow in this notion. And there's a lot of things you can give examples of what different kinds of TRDF you can have. Okay, so light sources. I will go a bit quickly over this one. This is really just an example. This is example light sources that you all want to simulate. It's much different from the classic point light sources that you had in your ray tracer. That's a TV, that's some flamingo thing, and a classic light bulb, and this searchlight. So forget about point lights. I said this before. What you're caring now for is, from now on, every location X can send light into every other direction, and there is an emission function, LE, for X, for omega, that just tells you how much. So if you think about the point light, that would mean that there is a certain location somewhere in space that for all directions, LE is a certain value, and for the rest it's 0. So I make yellow here for something where it's non-zero, 10 or whatever this is in some fantasy units, and it's black for all the other stuff. I'm not saying it's only non-zero for one direction and one position. That would be some crazy laser pointer, but it's at one position and it goes in all the directions. So that's a light source, like an omni light source in ray tracing that sends light everywhere. But you can do more general things. So in this case, the emission is 0, except at all points that are on the TV, and now they're for all the directions. So now it's not a point, but it also supports that you can have arbitrary positions. And the color LE that it is there, it also depends on the position. So if this would show some maybe blue pattern on this stuff and red pattern here, the spectral components of LE and LR, the spectral components would be reddish here and bluish here. So it also supports light sources that change the color over their surface. How to get that into the software system? I will not talk about this. This is computer programming and so on. We will see this later. But for today, this is just a formal thing. And that's another interesting thing. That's this something like a very strong light source that has maybe a non-negligible surface area. So it has many positions X where it's non-zero, but it's 0 for lots of other directions. So in this direction, this thing would look black. Yeah, it's not emitting light in that direction. Everything is being sent here. It still appears bright because of other effects and so on, but compared to the light that it sends forward, the light that goes into other directions is really minimal. It's the same thing like the projector in that room. Yeah, because I'm not glared by it. I don't see the light going there. Yeah? I see the point, I see the X, but I don't have the right omega. If I stand there, then I will get the light. I will not do it. Yeah, but then I would get the light. So that's really different, and it looks similar in the beginning, but as long as you do your LE right, it can express lots of things. Questions on this one? No? And the next thing that adds complication is the spherical integration. So it's very easy to write this this integration thing there. So I just recap for myself. The classic thing that most of us know, if you have a function f of x, this is x, your integration domain is maybe just scalar. You have f of x, and the integral is maybe the area, this blue stuff under the surface. Yeah? The slightly more generalized thing is you have 2D, you have y and x, and you have f of those two things. F of x is a value, and then the volume, I had a hard time drawing this, of 1, 1, if you integrate the unit area as if you do the unit area, unit piece of unit interval here, you will get the volume under this strange shape. How to get this? It's a different question, but this is what we're interested in. And in the end, what we're doing is also two-dimensional, but it's not on the domain of, it's not on the three-dimensional domain, but it's integrating over the entire sphere. So you have a point and you go over all the direction. That forms a sphere. And what you're interested in is there is a function defined on that sphere. So that's basically the height, so to say, on the spherical surface. And that forms a function. And if you integrate everything up, that gives you the value. This is what spherical integration does. Yeah. You can do those things analytically, so I can tell you when I come with a disk in this orientation or some anisotropic disk of a certain size. And you could even sit down and do all those integrations. Because it's 2D, I think there are some laws that you first do it over x and you do it over y. And there are certain theorems, Stokes' theorem, for example, we talked about this. You can go over the boundaries of light sources and get this still holds in the spherical domain. Why not? There are little tricks that you can do. But in reality, this function will be far from anything analytic like a polygon or something. In reality, what you have to imagine is this is all the light arriving at the point. This is almost like when you sit somewhere and you look around you and you see everything and you're integrating that up. So no chance, in the same way like you cannot compute the image analytically, you cannot compute the integral of the image or the integral of anything that you see in reality analytically. Still, this is what you have to do. Yeah? Okay. But I mentioned Stokes' theorem, that doesn't work. What would be, I mean, you're good at math. What would you do then if you can't do something analytic?
Approximate with some
numerically, just taking samples or like taking it into pieces, like that's a typical thing, that you just split it into little pieces, you approximate them and you just sum them up. So you would say, oh, I take this into little pieces and I sum them up, and we will see that the methods that solve this, they proceed in such a way. So no chance of doing this analytically in any non-trivial case. Yeah. Okay, and the other thing, I hinted at this already before, so what is y? Where do shadows come from? So again, y is this point. When you are somewhere, you're integrating up all the directions, you multiply with the reflectivity. This would tell you this is the point along this direction, which is the first one, yeah, before anything else. And it's exactly the same shadow test that you have in ray tracing. So if you have your ray tracer, that's good, because it's easy to say what this point is in a formula. I just write y, but algorithmically, how to do this? This is adding all the complication algorithmically. It's all the computational effort, because you saw computing those points is slow. If I give you a world with millions of bunnies, how do you know what is this point that along some point in some direction is the closest point? This really takes long, these kinds of theories. So they are computationally the thing that is hard. When I give you x, give me y. And they are the source of infinite frequencies, and this makes it very hard to solve this integral. If everything would be solved, there are certain theories of continuity and so on that tell you that if you make some kind of effort, it will be bound what the error is that you will get. But because visibility adds you infinite frequency, so if you move with that point a bit just here, at some point you will all of a sudden, like really in a blink of an eye, like really infinitely small, you will all of a sudden get a very different y, which is totally different and could be bright all of a sudden. This guy could be black. Just move a little, and you get like a total step, hard edge change of your function that tells you what's the light coming in. And dealing with functions with infinite frequencies or like no band limit and so on, this is usually, yeah, this is very hard. There's no, you could not even imaging with a sensor. You will always get aliasing and all kinds of problems and noise when you have something infinitely fast changing. Yeah, if it was smooth, you just change it a bit, and then there's some gradual change from a value into another. You can hope that with some effort you will manage. But with this, you will always have some remaining error, and this is exactly because of that guy. This is causing the problem. Questions on what y does? Yeah, please.
Recursive integration is recursive because
who is recursive?
Because to know the radians, we need to integrate for the radians in another point,
yes.
But we can know.
You don't know it. That's like really the problem. It's not like if you want to compute this, you know this, you hold it fixed, and you just evaluate your integral. It's not working like this.
Yeah,
I don't make any I don't propose a way to solve this yet. I'm just describing you how it is. Yeah.
Okay. To calculate the radians from a point, we need to.
If you are able in a forward way to calculate the value, you already have to have it.
Okay.
That's evil, but that's the only thing I can say. If you're able to calculate this, if you really ask me like this, how do I calculate this? you have to have this stuff. And if you have this, you have L. Yeah? And you have to have this one here. And it's just in a different point, but there's nothing, for example, that prevents you from saying, oh, I see myself in a mirror, so if I know my value, I can look up myself and so on. It's just all recursive. You just have to find the entire function such that then it fits together. Then you have it. It's just that complicated. You can make simplifying assumptions and just say, I have all those guys. Ray tracing does. Ray tracing says L is always 0 except at 3 points, where for all omega it's just sending something. That's some simplifying assumption how old ray tracing solved this. But it's not correct and it will not give you all the light paths that you could have. Okay, question on y. Maybe remember where it is in the equation. It's this point we were getting the light from. The Ly in there. So x and y, there are different points. So it's the same function. Okay. So, and the thing which should be really new to you is this function that basically translates the incoming light under the integration into how much it contributes to the outgoing light, and this is called the bidirectional reflectance distribution function. And it's defined as the radiance reflected in direction omega, O from an irradiance at direction omega I. Irradiance is a slightly different quantity than radiance. We will not go into this, but it's integrating over solid angles and so on. This is for the math. I will not go into this. But the important thing is just, roughly, this is what you should remember. If some amount goes in, some unit amount goes in, how much goes out? If it's 0, it's black for this combination of rays. If it's infinite, it would be behaving like a mirror. And there are certain laws that it has to fulfill. So it should not be negative. It will never take away light. So it will never make something look bright. If something else is like not sending any light or something, it's never like this. It can just reduce something. So it's energy conserving. So if you integrate over the entire thing, if you look at all the directions together, at most this can send out as much light as went in. If you have a very high albedo, this thing is called albedo if you integrate it up, then you have almost 100%. It's very hard. You cannot manufacture something like that in reality. In reality, it's more like 0.8. And it's not interesting what the value is for a point. This can be very high, but it's like a probability distribution functions. They can be very peaky and very high above 1, but the integral is 1. And in this case, it's just at most 1, because at most you can get all the light that you send in back. And there's another property of BRDFs that is a bit surprising, but it simply holds, and it just says, when I see something from a certain direction, how much I do see the light source is the same as when I would start from the light source and how much is being reflected to me. You cannot make a material that treats light differently when it comes from this or it comes from this, because in the end everything is a mirror, and all of this is just aggregate statistics, so there is no way of making something non-reciprocal. Yeah? So this is always little things that you have to check when you use your BRDF model or something, and you write it down. These are properties that it should have. So maybe integrate it up. If it then turns into 5, things get brighter and brighter. So light is bouncing, so you get 1 unit light in and you get 5 out, then it will get brighter and brighter and it will not converge. It's exactly only if it's smaller than 1 this thing is converging, because otherwise light would bounce and it would sum up and so on. This is not how it behaves. Yeah. Okay, questions on this? Speed a bit up. This is examples of how these things typically look like. So mud materials, it would be plaster, and even rubber falls into that category. For this BRDF, we talked about that this would be a constant. It's not like the dot product, it's the constant. The dot product is in the rendering equation anyway, so here the dot product, the BRDF is just a constant. You have other materials, all those specular materials. You've seen the metal and you've seen plastic, glass, all of these things. These are BRDFs, which are 0 for most of their domain, and then just non-zero in some areas which are around this mirror directions. We will see examples. And this is so general that it can even model velvet and brushed metals and so on that show you reflection patterns such as this one. So if you have a point light source, they will start to reflect like very complicated ways, and the highlights are shapes like this one here in the middle. See this? Yeah, this one here. They're really very far from what you can expect from foam, which is usually this Gaussian little bump, and these. And they're important for like satin, so for clothing. It's still not solved how to render this like very well for the fashion industry and so on. And there are even more advanced things like translucent material that go beyond that, where the light is entering in some position. So maybe, for example, behind this little cow's ear here, and it's then transmitted through the surface and comes out of at the other end. This is even beyond what the BRDF can do. And it's not what we're going to do today, but this still exists in reality, so it's worth mentioning. So The full BRDF is a 4D function. You remember, it's somewhere defined, and it translates from a two-dimensional, at most two-dimensional angle of coming in how much is going out. So that makes 4 degrees of freedom. And there are different kinds of models that will just simplify this entire thing, Phong, Ward, and Lafortune. We've seen how Phong works, and all of these others. I will not give the formulas, but you can imagine they are similar like Phong. Lafortune, for example, is just adding multiple lobes together and so on, and all of them get closer and closer to reality. But I'm personally usually am happy with Phong. So if you solve your rendering equation with the Phong model SBRDF inside, you already can get something pretty decent, I would say, for the beginning. And let's stick to Phong at that moment. So let's recall how this would look like now in this theory. So if you have some incoming direction, and this is a perfectly diffuse material, the value of that function would just be a plane constant. So whatever comes in from that direction, it's reflected into that direction in the same way. Yeah? The fact that it gets darker is because of the other cosine term. And then by people, if you integrate this up, because it's a constant, people call this rho, this is called the albedo, and if this is 1, it's like perfectly white, and if it goes to black, it gradually gets darker, but no directional dependence. And what you saw before in ray tracing would be something I cannot draw, so that's 0 everywhere, and it's infinity in exactly this mirror direction, and if you integrate this up, all those things hold. That's the properties of directs. But in practice, it's very complicated. You cannot use it. You cannot work with infinity, so you have to find other ways of dealing with this. What you do then is, because that's also what happens in reality, no mirror is perfect. All of them are glossy to some extent, and we have seen how you can, with this glossiness factor, make lobes which are very, very narrow with the glossiness factor when you take the dot product between reflected and viewing direction to a power, and you just take a very high power, this guy gets narrower and narrower and very, very peaky, and then it's almost like a mirror at some point. And this is some moderately glossy object, maybe a not so polished metal ball that you see here, where you have some form of lobe around it. And in practice, it's more like this. So you have some diffuse part and some specular part, and this is what you, similar to what you had as plastic in your ray tracing exercise. Yeah, and it's more general. It can also do things like this. So if you walk around in London, sometimes you see those retroreflective things on the vests of people. This is light when it comes under the reflection angle. The bicycle drivers, they want to be seen. But ideally, multiple things should be very bright. So you have these little microstructures that also make light being reflected in the direction where it comes from back. So if it comes at you, it has a lobe which makes it very bright if the light goes back into the same direction. So if the headlight is shining at the bicycle driver, it's very quick, very strongly also getting back and scatters back. And you can do this with some additional lobe that you can make. Yeah. So the textile manufacturers, they try to make this very, very peaky and very strong so that people are exactly seen when you shine light at them. And then you call that retroreflective. And there are other models that can do this. But all of this is just different ways of setting up equations together here. Yeah. So you either set up your model. What I showed to you was basically still Phong, except the last one, and you just choose model parameters and select them. That's one option. The other thing is you could measure that, and you could also get that from photographies. I just want to show you an example of how to measure it, because that can be huge fun, and some people here are doing it. If you have a small piece of sample and you want to know what's the BRDF, you construct something called the gonio reflectometer. So this is just cameras and light sources, and they can basically sample all the angles. So you just put the camera for one angle, that's the outgoing angle, you just put the light somewhere and you take an image. And then you have 4-dimensionally many images. You can move the camera to all 2-dimensional angles that you can have. You can move the light to all the positions that you have, and all the 4-dimensionally many combinations. They give you a table that exactly tells you the BRDF. So if you really want to do it perfectly, say for textile design, you put your textile sample here, you wait for half a day, because then it does some motor motions and it gets hot and many things are complicated and it's dangerous and you should stay away from it, and it shoots lots of flashes and takes lots of photos, and then it gives you something in the order of, you can imagine each one is an image, and you have 4-dimensionally many, so even if you have 100 here, you have 100 here, that's 10,000, and that's just 2 of the 4 dimensions, and so you should think a bit on how you sample this and so on. It's an art on its own. And you should also not forget, so what I explained to you now was really the BRDF. The BRDF, what most people call the BRDF, is just this. Because we didn't consider into that in some other places, it all of a sudden might be a very different material. So there's nothing that prevents you on making like a biker vest, which is retroreflective and then it's diffuse. It's retroreflective, so if you move around the surface, those behaviors might change. So if you have light coming in from one direction and going out in another, it might be different between 2 different points. And then this is called spatially varying BRDF or SVBRDF. So the thing which is really in the rendering equation is the SVBRDF, where you have a coordinate where these behaviors are also modulated depending on where you are. Yeah? So the reflection might change from location to location. And here's an example of this one. So this is rich in appearance from Microsoft Research Asia, really cool paper that's looking rich in appearance, not because it's so complicatingly depending on the incoming and outgoing direction, but because it also changes over the surface. So I have to stop at some point. Yes, I think.